Okay, dear friends, Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India, initiated by myself in 2017. And we used to organize several online programs to help the students who are preparing different national level competitive examinations like CSER, NET, GATE, IIT, JAM, NBHM, etc. As a part of that series, as all of you know, on the next Sunday, we are having the TIFR GS 2025 examination. So we are organizing a 1 week crash course for TIFR exam. We have Mr. Lalit Thuwal as our resource person for this crash course. Mr. Lalit is currently pursuing PhD at Indian Institute of Science, Bangalore. He qualified all these type of exams with with CSER net with all India rank 4, and also qualified GATE, NBHM, extra. So, and also, yeah, I would like to appreciate Mr. Lalit for his uh, initiative to help the juniors preparing for this type of competitive examinations. He used to upload several videos, this type of problem solving session videos on YouTube. And actually he is very passionate as a teacher, as a mentor, to help the juniors. So it is my pleasure to welcome Mr. Lalit to Math Aspirants platform. And also, I would like to express my sincere gratitude and thanks for to Mr. Lalit for being with Math Aspirants and for also agreeing with me to handle such a series of problem solving sessions. I'm sure that these sessions will be certainly helpful to all those who are seriously preparing for TIFR exam. And I would like to wish all the participants a great success in the examinations forthcoming. So, with these words, I welcome everyone to this program, and also I would like to welcome Mr. Lalit to handle the session. Welcome, Lalit.
Yeah. So thank you, Professor, for the kind introduction and giving me opportunity to interact such a motivated group of students. So you all must have gone through the outline of the course said in the group. So let me quickly recap that what we'll be doing in next 7 days. So for the first 4 days, we will be focusing on solving the problems from TFR previous year exams. And in addition to that, I will also posing the problems here made by myself. So on the 5th day, I will conduct a mock test that mirrors the TFR format and giving you opportunity to practice your strategies and time management. Uh, for the next 2 days, I will keep it flexible, okay? Based on the test results and your preferences, I would like to decide in a day advance that whether to focus on additional problem solving sessions or advanced concept or is addressing your specific doubts. And however, we will solve key problems together here. It's not possible to cover all the previous year problems from the TFR exam, but I will certainly guide you that how to solve a certain type of problems and how to think the solution of the problems. Okay, I will not only be letting you know that how to what is the solution of the some specific problem. I will also let you know that how you yourself can think about the problem. What is the natural approach that leads to the solution directly? Okay, but at the end of today's session, please remind me if I forget. I would like to share some reference videos where I have solved the complete exams in detail. So I would say that you can review them in you can watch them in your free time to supplement what we discuss here. And reviewing those videos before coming to the next session will be very helpful for solidifying your understanding. Okay, so let's begin with today's session. So it will take me 1 minute to join from another device. I will present then. Okay, so give me 1 minute, please. So can you see my screen?
No,
Not
sir.
yet, right? Not yet. Okay. So I think. So someone is unmuted. Yeah. So now you can anyone of you confirm that you can see the screen? So am I audible,
Yes,
right?
sir.
You can
Yes,
hear
sir.
my voice clearly. Okay, so let's start. Yeah. So this is the problem asked in TIFR 2024 exam. So what this question says, see. Okay, so let f is a function from R to 0 infinity. This is just a function, okay? Need not be continuous, any function, such that for any finite set E, any finite subset of R we have. What does this mean? To solve a problem, you must understand that what a question is saying. Okay, if you don't understand that, it's not possible that you will solve that. So it says that whenever you choose a finite pick of finite subset of R, say it has to understand finitely many points, say just 3 points, okay, and you take the sum of functional values, then that must be less than n equal to 1, no matter how large your finite set is. Okay, so let then CF is the set of those x where fx takes strictly greater than 0 value. Okay, so what you have to tell here that please keep in mind that this is a MCQ question, and in MCQ in TFR there is only one correct option. Okay, so there are some smart ways you can save your time in exam. Okay, so I will tell you also that. So then CF is finite, CF is a bounded subset of R, CF has at most one limit point, and CF is a countable set. So see, first of all we will say that the first one is wrong, right? Can anyone of see why we will say that the first option is wrong? Because if the first one is correct, the second one must be correct, because any finite set is bounded and there cannot be two correct options in a TFR exam in part A. So that is obviously not correct. Okay, so we will think about the another VCD. So we know that this first option is not correct. This will lead you to the solution. So you can construct an example of a function which satisfy all these things, but that function takes value greater than 0 at infinitely many points. Okay, how do I construct such an example? So okay, so how do you think? So think about a function f which takes value, say some of the convergent series like that, 1 by 2 square, 1 by 3 square, like that. So you can pick arbitrary points from R, say x1, x2. This is the way to think about this problem. Okay, so say that your function takes value 1 at x1, your function takes 1 by 2 square at x2, and your function takes 1 by 3 square at x3, and so on. Okay, so there are only countably many points where the function is taking non-zero value, but at all other points it takes the value 0. Okay, then whatever function satisfies, but I have to make here some adjustment. Okay, why? Because you will understand this 2 pi square, 3 pi square, dot dot dot. Now what happens is that whenever you choose, so how I define my function, that it takes the value 1 over n pi square if your x is, say, you can pick any countable set. Okay, whatever your need demands. Okay, so let me write here now n, so n otherwise 0. So in this case, what happens is that you see, whenever you choose a finite set, say E is any finite subset of R, so it has finitely many points, right? Say A1, A2, dot 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 An. Okay, say, and you consider this sum FA1, FA2, dot dot dot. So by our construction, our function is taking non-zero values only at natural numbers. Okay, so this sum is always going to be less than n equal to the sum of all the values where function is non-zero, right? Right. So n goes to 1 to infinity 1 over n pi whole square. So this comes out to be So do you know what is the sum of this series? Anyone of you want to let me know? What is the sum of this series? So, you know, right? Summation 1 by n square converse.
1
I
by
have made
6.
Yeah, 1 by 6, right? So 1 by 6. This is obviously less than or equal to 1, right? So all the hypotheses of the question are satisfied. And we see that the function on the net set of natural number takes value greater than 0. So in this case, CF is this. So the first option is not correct, and the second option is not correct because CF need not be bounded. And the third option, CF has at most one limit point. Now, how can we counter this? Yes, obviously we can counter this. Now we try to, as I said, that we can, here we can take any countable set, right? So what I do now, so mixing all these, I am going to construct one example which will eliminate all the three options. Okay, so how? So, and the example, how do I think about this example? This comes from all these things. Okay, you will understand this. So how I define this? 1 by n square n pi whole square. If your x is, so I want to make CF is such that it has more than one limit point. Okay, so here I do this adjustment that if x is this or 2 plus 1 by n or n or some natural number. Okay, for some natural number this, otherwise it is 0 everywhere. Okay, so now see, let me show you that it satisfies the hypothesis, okay, of the function. Suppose E is some finite subset of R, and you consider this sum x belongs to E fx. So what I'm going to do, I'm adding all those values where function takes non-zero value. Okay, so this comes out to be 3 times 1 summation 1 over n pi square. So can you see this? Why this happens? So I have added here all the values of the function, functional values, right? I think it's clear, right? So this is going to be 1 by 2. This is strictly less than 1. So all the hypotheses are satisfied. Can any of you see that what is CF in this case? What is CF in this case? Yeah, please. You can raise your hand if you want to answer. I would like to make the sessions interactive. So just you have to see that where the function is taking non-zero values, right? Where it is taking non-zero values. It's easy. See, 1 plus 1 by n, n is in n, union 2 plus 1 by n, n is in n, and union n, right? Right? These are the only point where your function is taking non-zero positive value, right? So in this case, can you see that this example discard all the three options? 1, 2, 3. First one is discarded because it's not a finite set. Second is discarded because it's not a bounded set. And the last one is also discarded. I mean, the last one, it is wrong. CF has at most one limit point because 1 and 2 are its limit points. So all three options are discarded. So we remained with only one option, D, so it must be correct. Now, in exam, you have solved it just using your elementary knowledge. But why it's countable? Now you know that it's a countable. How do you prove that? So whenever you want to prove something is countable, what do? There are, standard procedures. You sometimes want to show that you have a set and it can be embedded in a countable set, right? That means that you have a one map from that set to some countable set. Or another way is to write your set as a countable union of countable sets, and that's the thing we use a lot of times. Okay, that's what I'm going to use here. So why CF is countable? See, so CF is uh, those values for which your fx becomes greater than 0. Okay, so I will define Sn. Define Sn. Sn is a set it consists of those real numbers where your function takes the value greater than 1 by n, right? Because if something is greater than 0, then that must be greater than 1 by n for some n. Okay, so do you see, can you see that this these essence cover CF? Right? Each SN is in CF, right? This containment is very clear, right? Because each SN is a subset of CF. But on the other hand, if you have some element in CF, that what does that mean? That means that say some element A, specific A is in CF. That means that it takes the value greater than 0. Then you have a real number which is greater than 0. Then by Archimedean property, or the convergence of sequence 1 by n to 0 will give you that for some m at least, not at least, for infinitely many m. So for infinitely many m, but we need only one. So for one natural number m, you can do this, right? Then this a lands inside Sm, right? So any point of Cm is also in this union. So this CF is equal to this union. Okay, so now so can you see that each SN is countable? In fact, finite. So in fact, finite, and it has cardinality. You can tell that it has cardinality at most this, right? Okay, let me show. So suppose you have some particular SN, okay? So it cannot be infinite, because if it is infinite, then you have infinitely many points, say, right? So let me fix, say, SM is finite, okay, for some m. SM is infinite. So for the sake of contradiction, I assume that SM is infinite. So what happens is that if this is infinite, then you have infinitely many points inside it, right? And for each AI, you have this, right? You have this, no? By definition of SM. So just add only m plus 1 points, only, right? M plus 1 points of this sequence. So this sum is at least so m plus 1 of m, 1, right? Because we have here m plus 1 quantities which are greater than 1 by m. So this comes out to be greater than 1, which contradicts the hypothesis of the question, right? So our assumption is wrong that each SM is infinite. So you must have understood that what can be the cardinality of SM? It's finite, right? In fact, you can tell what is the cardinality from here. Okay, so that doesn't matter, by the way. So here we see that CF can be expressed as a union of countable sets. Okay, and this union is countable, so it must be countable. So in this way, so first I have eliminate all the options. The last thing what I have told you, usually you cannot think about it in the exam, but you can eliminate options in the exam, right? And when you come back to home, you can solve the problems. Okay, so in this way, this problem is solved. Yeah. So let me move to the next question. Any quick questions? Yeah, you can ask me the questions at the last, okay? If you have some questions like which will take the time, otherwise we will not meet our goal. Okay, so this question. Okay, so this question is very interesting. You might have solved this before also, but I'm going to let you know a very simplest and a very quick way to solve this in the exam. Okay, so in exam, you have to be very quick in solving. Okay, so not in the TFR, but there are some other exams, CSIR, NET, GATE, where your quickness matters. But in TFR, this does not happen usually. In TFR, you will have enough time. If you have prepared well, then you will have enough time to solve questions. But solving problems quickly will really going to benefit, right? So how do you solve such problems? So anyone want to give me some idea to solve this, that we can solve like that? Only idea, okay? Or just the solution? You can raise your hand whenever you want to ask, say something. Okay, so some of you, okay, let me read the question first. Okay, so what this says that R is this quotient ring. Okay, so some of you are unmuted, seems to be unmuted. You can mute. Okay, if you want to ask or tell something, then you can just raise your hand. I will answer your questions. Okay, so R is this quotient ring obtained after the quotient of the polynomial ring Cx by the ideal generated by x square, right? We all know this. So let R star be the multiplier, because this is a group and you know that the all set of all multiplicative units forms a group. Okay, that is denoted by R star. This means that this is just this. Okay, so this. So what, this is a true false question in the 2024. Okay, this is of part B. You have to determine whether or this is true or false. Okay, so see what this says. Then there is an injective group homomorphism. Injective group homomorphism from your Z2 cross Z2 to your R star. Okay, say R star. So you have you want an injective homomorphism. You want to check for an injective homomorphism. What does it mean? Whenever you have an injective homomorphism, say that Z2 cross Z2 has 4 elements, right? So it will be its image. Oh, sorry. Uh, Say its image. Then just forget about this one. This Z2 cross Z2 will be isomorphic to image, right? Its image. So we can say that R star contains, R cross contains a sub, if such a homomorphism exists, injective group homomorphism exists, then we then there must have a R star must, sorry, R cross must have a subgroup isomorphic to Z2 cross Z2. That, what does that mean? If it has a subgroup isomorphic to Z2 cross Z2, that means that it has a subgroup like this, 0 AB. It is already commutative. Okay, so if you have two elements of order 2 here in R cross, then you have a subgroup isomorphic to Z2 cross Z2, and you are done. So you just have to know that whether or not this R star has elements of order 2. But for that, you have to know how R star, I'm saying R star because I'm used to denoting it by R star. So forgive me. So this is R cross. So, right. But how do you know what is how R cross looks like? Here is the quickness comes into play. Okay. So now someone will solve this. Okay. There are two ways from here to solve. Whether you just first observe that this ring is just look like this. Okay. I'm writing it here. If you can see, this ring will look like this: ax plus b, ideal generated by x square, where a and b are elements of C, right? So you want to know that what are the units among them. So okay, so let me tell you, how do you know quickly? So quick way to know. Okay, you can just do that by calculation also. Okay, but that will take your time and will trap you into calculation. I don't want that. Okay, so what I use, correspondence theorem. So by correspondence theorem, right, the ideals of this, there are exactly three ideals. This is a local ring. Okay, there are exactly three ideals. Why? Because this is a PID, right? Any ideal which contains this. First of all, what correspondence theorem says that if you have a ring R modulo Y, then its subrings looks like this. Okay, so they I'm using correspondence theorem here. So first of all, I want to know that which ideals contain x square, because this is a PID. So if some ideal contains the ideal generated by x square, that must be generated by some divisor of x square, right? The divisor of x square is x1 and x square only. So there are exactly three ideals of this ring. So two of them are trivial. Okay, they are always. So one is this non-zero proper ideal. Okay, so this is a non-zero proper ideal. So I say that in R, there is only one non-zero proper ideal. Non-zero proper ideal. Okay, so there is only one non-zero proper ideal, so that is generated by X. So X like this. So this element will generate that. Okay, so here are, so this will look like this AX, right? Like this AX plus X square. A is in C. So can anyone of you let me know that what will be the units of R now? I have told you that there is only one non-zero proper ideal, or you can say that there is exactly one maximal ideal in this ring. So can anyone of you see that what will be the units? You must have seen this phenomenon in algebra. When set of all, yeah, it is, you want to say, I think. No, here is something. Okay. Okay. So if you have a ring, you have a subring, okay? Such that whenever something is outside it, then it's a unit. Okay, so let me tell you. So there is only one maximal ideal. Anything outside that maximal ideal will generate the full ideal. I mean, that will be the unit, right? If you have a ring R, say I is the ideal, which is only non-zero proper ideal. What does that mean? If you take some element from R and generate the ideal, and this is outside I, so this ideal must be equal to R when ideal generated by some element is equal to R, when A is unit. So it means that any element I outside I will be a unit. So any element which does not lie inside this will be a unit. That is, so in this way, you quickly find that the units of your ring are such that, okay, this is a coset, X square, and B must not be 0, because if B is 0, then it goes inside this ideal. This will be in the ideal generated by X, right? So this is the set of R star. Now we have known what is the set of R star, set of units of R. So let's find that what are the elements of order 2. Okay, so if you want to find the elements of order 2, you can make the calculation. That's very easy. Just put it unit, and it will give you that these are the only elements which satisfy. I mean, -1 plus X square is the only element of order 2. Okay, so we have found, so thus we found R cross has only one element of order 2. Okay, only one element of order 2. On the other hand, we have here three elements of order 2. So there does not exist, cannot exist an injective homomorphism from this group to R cross, right? Because an injective homomorphism preserves orders, right? So here you have only one element of order 2. In this way, this statement is false. Okay, right? Yeah. So, okay, by the way, I want to ask some questions. What I said that I will give you some problems also. We will not be solving only TIFR previous year problems. I will be asking you some interesting questions also. So there is a question for you in the first question. I forgot that. So let me ask it here. So about the countability, let me ask a question. Okay, suppose you have the set natural number X, and X will be the set of, this is the set of uh, subsets of n with infinite complement. So is it countable? Is it countable? Yeah, you can think. I will give you at least 2 minutes. Such questions are, very necessary. Whenever I will solve some problem, then I will ask a question. You can think about it, okay? It's not necessary that you will solve, and I would not accept that you answer me. Just think about it for 2 minutes at least.
Sir, what
So
does
raise
it
your
mean
hand.
by?
This is a subset of a set of all subsets of n, right? You have the natural number, set of natural numbers. Then you have the collection of all those subsets of natural number which has infinite complement, whose complement is infinite. Is it clear, right? No.
Yes, sir. You means a finite subset of X.
No. That doesn't need to be a finite, because infinite subsets can also have infinite complement. For the example, you can consider set of all even integers, natural even integer, that has infinite complement, but itself it is infinite, right? All finite sets will be there, right? But there will be more.
Sir, we can construct a countable collection.
So do you think that this is countable? Okay, so some Vijay.
Yeah.
Yeah. Okay. So by the way, some of you raised the hand. Yeah, Vijay. What is your
Hello.
answer? Yes, Manoj. Is it countable?
Sir, we can think it about like all the
So what?
subset of 2n and it is infinite. So,
Right.
oh,
Right. Yeah, that's the good argument. I expected that. Right. Very good. So you can just pick first 2n, and all the subsets of 2n will have infinite complement, right? So they are uncountable. So at least we have uncountable subsets inside that. So it's uncountable. Okay. So good. So now let me come to the next question. So in this last question, we have seen an example of a local ring. A local ring is a ring which have exactly one maximal ideal. Okay. So now let me ask a question that do you think that Q has a subring which satisfy this, say subring S between Z and Q, which is local? Okay. So after each question, I will ask a question and we'll give you 2 minutes. Such kind of questions will be really there in your exam. So you have raised the hand again, or it was already raised? Manoj, you want to answer this question?
sir, actually, I forgot the definition of local ring.
Yeah, I have told the definition of local ring. It has exactly one maximal ideal. Okay. So now it's your homework. I will ask you tomorrow all that. Does the such a ring exist between Q and Z, which has exactly one maximal ideal? Okay. So think about it. So let me discuss the another question from TFR 2024. This is also very interesting, and I will ask you a very interesting question about irreducibility after this. Okay, and please be with me. I'm asking you very really interesting questions. At the end of this session, I will ask you a very interesting question. There, you will like that. Okay, so sorry, sir. Sorry, sir. So what is given to us that if A is MNQ, this is a matrix of n cross n with rational entries is such that the characteristic polynomial of A is irreducible over Q, right? Irreducible means that you cannot factor it non-trivial over Q. Then A is diagonalizable in MNC. Okay, there exists, this is just the definition of diagonalizability. So here you will use a result that A is a matrix A in MNC is diagonalizable. It's diagonalizable, and you should know this result. Okay, this is very important, and it will be always used in the questions of diagonalizability. You can see that whenever you will be solving problems of diagonalizability in these types of competitive exams, you will find that you are using that result. Okay, so if and only if minimal polynomial let me write it. 𝕃𝕒𝕒𝕚 has no repeated roots. Okay. No repeated roots. Okay. So solution is that first, when you are in the exam, you will try to think about some counter example, but you will not be able to counter it. So now you know that the characteristic polynomial is irreducible. So if it would be diagonalizable every time, that what does it mean? That if characteristic polynomial is irreducible, that means that is minimal polynomial also, right? Because minimal polynomial is what? Just say Cx is mx divides Cx, right? Minimal polynomial will divide Cx, but Cax is given to be irreducible over Q. So what does that mean? That means that mx is equal to Cx, right? Because a irreducible polynomial means it does not have non-trivial factors. It's like a prime number. Okay, so now you want to see that whether a irreducible polynomial always have distinct roots, right? So now our problem is reduces to check this, right? Okay, let's check this. Okay, so because our guess will be that it has, right? Because we have already tried for the examples for non-diagonalizability, but what will turn out that you will see that always distinct roots are there. Okay, so to prove our guess, so for the sake of contradiction, let me assume that alpha is repeated root. Okay, repeated root of mx. So I will denote it by just fx now. Okay, I don't want to write a again and over again. So or just mx, maybe I will skip a. So what happens when mx has a repeated root? This is just a calculus. Okay, you must let me know this. M alpha is equal to 0 also. M dash alpha is 0, right? Derivative also must vanish at that point if it is a repeated root. Okay, so see, mx and m dash x are elements of qx, and is very useful. You must have seen it everywhere. Whenever you are discussing about the modules over PID, you will see that this is used a lot of times. Okay, so it is very important property. So what is that? In a PID, what we can do? Let me claim here that GCD of mx and m dash x is 1 because mx is irreducible, right? And GCD of a irreducible polynomial with any polynomial is whether mx or it must be 1, right? It's like a prime. GCD of a prime with any number is either that prime or just 1. Okay, so in this case, the degree of mx is less than mx, right? So the GCDs must be equal to 1. So because QX is a PID, we can express GCD as a linear combination. Okay, for some P and Q in Q. Okay, fill the details. Okay, you can write for some P and Q in Q. Right, but now substituting alpha will give us what it will give us: M alpha, Q alpha, M dash alpha, P alpha is equal to 1, but that comes out to be 0 equal to 1, which is absurd, you know. That cannot be. That cannot happen. Okay, so why this contradiction? Why do we arrive at this contradiction? Because we have assumed that there is a repeated root. So our polynomial mx does not have a repeated root, and we are done. Right? That's what we wanted to prove. So what does it mean? So mx had no repeated root. It means our polynomial is going to be diagonalizable. So this is a true statement. So any question? Any quick questions? Okay, So yeah, TIFR 2023. That was of TIFR 2024. Now you must answer this question. How many of you can answer this? This was in TIFR 2023 and this was asked in TIFR 2024. Assume for a moment that one student solved this previous year problem, right? Then he must know that about this, right? In the 2024. So we are solving previous year problems. So you may expect that in the TIFR 2025, you will find some problems which have some connection from the previous problems. Definitely, it always happens. Okay, so take these sessions seriously. Okay, so yeah, uh, how many of you can answer this? That this is a true option or not? Raise your hand if you can answer. Just raise your hand, okay? I want to see that whether or not you understand what I. Yeah, you don't have to tell it, okay? Just raise your hand. I just want to see that how many of you understand what I just told you. Okay, but you can raise your hand that, okay, we don't have to answer, so we can reach. Don't do that, okay? I may ask you. So, okay, so very good. So many hand raised. Okay, so let me ask. Okay, Sayan, there is someone named Sayan. Okay, you tell. What is this? Is true or false?
Sir, this is true.
Why?
Sir, because x to the power 4 plus 1 is irreducible in a rational.
Very good. Very good. The questions are same, right? So
Yes, sir.
yeah, this polynomial is irreducible. Is irreducible. You can say that the problems are same, right? This is of 2023. That is of 2024. You know, if you will solve this, then you must know this fact. What I use there. Okay. So irreducible. So by above discussion. This is true. Okay. By the way, forgive me for this type of handwriting if you are not understanding this because I'm writing fast. Otherwise, I write very neat and clean. Okay, so right. Okay, let me ask you an interesting question now. Okay, so how many of you know about the Einstein irreducibility criterion? Raise your hand if you know about the Einstein irreducibility criterion. It does not take anything when you raise your hand. Okay, you just have to do like that. Okay. So many of you know, so I must ask you the question. Okay, so right, some of you afraid, right? You think that, okay, as far we have a polynomial ring in one variable, it's everything is fine. But when we have a polynomial in two variable, then we have problems to determine whether some polynomial is irreducible or not, quotient ring. So don't afraid with that. I am going to let you know a trick. Okay, a very good thing, not a trick. That is a standard procedure rather. So to decide that, I mean, you will learn something. Okay, very good. So this polynomial, we will discuss about this polynomial later. First, let me know that this ring is a field or not. Okay, just let me know that this is an integral domain or not. Okay, this will be an integral domain if this ideal will be prime. Okay, this ideal will be prime, then this is a prime element. In a UFD, prime element is irreducible element, right? So we are reduced to check that this is an irreducible polynomial or not. Okay, so okay, when I ask that how many of you know something, then you raise your hand because you know something. But now I will ask something different, that how many of you face difficulties to decide that polynomials will be irreducible or not whenever you deal with two variable case. Okay, so there should be no same in raising hand. Okay, I will let you know. Mathematics is infinite. If you don't know, that's okay. Okay, so you feel, right? Yeah, I have seen a lot of students to ask me that type of thing. Okay, so there are two ways. Okay, one quick way sometimes will help you, that see this as a ring. let me tell you that, okay, this is irreducible. See this ring like that. Okay, right? Isomorphic. These two are isomorphic, right? And you know what is the isomorphism. So now think this like R. Okay, Ry. Right? Ry. And write this polynomial like this. Okay. So we have a polynomial now with coefficient from this R. Now just treat them as constant. Like in ZX, you have a ring like x square plus 1 plus 2x. Then how you see these two elements of Z, right? Now see these elements, see these x square terms as an element of qx, as an element of R. Now we can here use Einstein irreducibility criterion. Why? Because in the same way you use in ZX. Okay, see, x minus 1 is irreducible element, right? Prime in qx. Everyone know, because this is irreducible element, so it is prime. You cannot reduce it, right? What will you do? You have no options. So see, this divides this term, right? X minus 1 divides x square minus 1. This does not divide the coefficient of y square, right? This does not divide, right? It does not divide. And when you square this element, this does not again divide this element, right? So this is a polynomial like this, and you have find an element in your ring R, which is prime, which P divides A, but P does not divide its coefficient, and you square P, then it does not divide A. Then you say by Einstein irreducibility criterion that this polynomial is going to be irreducible. Okay. So by the Einstein irreducibility criterion, this polynomial is irreducible. Okay. So this is one thing you can use in rings or with several variable. Okay. Another thing is, there is another thing you can also use. What do you use? Okay. Here you have to see this. Such questions might be there. Okay. I have seen such problems in TFR. There is a problem in TFR 2020 about the quotient ring of QXY, which involves observing that some thing like that. Okay, I will give you the reference about that video. Please ask me at the end of the session. Okay, I might forget. Okay, so right. So x square plus minus 1. What is another way? So now you again have to see it as a polynomial in here we see it as a polynomial in y, right? As a polynomial y with coefficient from qx. So now just see is a polynomial in x with coefficient from qy. Okay, now you will treat these type of terms like you treat the terms of z in the polynomials inside this. Okay, hope you understand what I'm saying. Understand like this Rx. So inside this we will have polynomials in x with coefficient from R. These will be assumed now coefficient. So suppose it's a reducible. So what is the possibility? The possibility is that you can reduce into linear polynomials. The linear polynomials will look like x plus b, x plus c. But here you have to keep in mind, these b, c will not be from q. They will be functions of y. Okay, because what I said, you are just seeing y square minus 1 coefficient polynomial in x. So this will be like this, cy. Now do the calculations and compare, and you will find that there is some contradiction. Okay, and this polynomial is going to be irreducible. Okay, so there are two ways you can use in such type of rings. Okay, that will be really helpful for you a lot of times. Okay, there is what I said. There is one problem of this kind of problem. So let me remind me at the end of this. I will give you the reference of that. Okay, where I have solved this problem in very detail. Okay, that will teach you a lot of things. So review that before coming to the next session. Okay, so let me go back to the next one. Sorry, come back to the next one. solution. Yeah. So what this says? This is the problem from TIFR 2023. You can, below your hand, okay? So if I ask next time, then raise your hand, I will think that you have reached. So, so A is in MNR is such that AB equal to BA, right? For all invertible matrices B in MNR. What does it mean? A matrix which commutes with all the invertible matrices, then A is a scalar matrix, right? So a lot of you must have known this, that what is the center of GLNR, right? So, okay. So suppose you don't know this, then you will try to think that definitely this scalar matrix will be satisfying this. Okay. Are there any other matrix? So you will, so what you have, see, you have a matrix A here, which is commuting with all invertible matrix. You have uncountably many choices, right? You can pick B anything and any element, whatever you want, according to your choice. That will show you that how the element of A will look like. Okay. So see, here I'm going to let you know the simplest way to determine it. But before that, you have to answer me something, or you don't have to answer it. Do you know that performing a elementary operation in a matrix, okay, you perform an, suppose you have the matrix M, okay, and you just say ABC, DEF, GHI. So if I perform an elementary operation on the second row, say, so do you know that it is equivalent to something, some multiplication, right? It is equivalent to multiplying the M on the left by the corresponding elementary matrix, right? When we perform elementary row operations, we are doing nothing. Then multiplying by a elementary matrix. And when we perform column operations, then it is equivalent to multiplying that matrix on the right by the corresponding elementary matrix. Okay. So this is what I'm going to use here. See, this is very easy and simple to decide. Otherwise, there are other ways by which you can decide that the matrix must be scalar, that by which you can determine that the matrix must be scalar. You will first use some special matrices, then you will use van der Waals matrix, right? A van der Waals matrix is also helpful in that case, but you don't need to do that. See, so your matrix, say B is this, okay? Just take general matrix. Okay, so to make you understand, let me take it off for the simplicity 3 cross 3. Okay, this will work in n cross n also. This is just for simplicity. So ABC, DEF, GHI. Okay, so if I multiply, perform a row operation, say in the second, not A, I will say now what I have not used, Y. Okay, YD, YE, YF, ABC. So GHI. So I have multiplied it by the elementary matrix, right? So perform the elementary row operation, right? Multiplied this row by Y. So this will be equivalent. But you know that suppose you have elementary matrix E, right? EB is equal to BE, right? Why? Because we know that we want to find those matrices which commutes with every matrix. So see, so this will be equal to A, D, G, performing the corresponding column operation. Okay, so you will perform the same operation in the second row. Here will be H, Y, I. No, it will be F. So C. So now, can you compare these elements like this? Compare Y, H with H. And this Y is any non-zero element. Okay, so Y, H will be equal to H. If H is 0, it's fine. If it is not 0, then what happens is that you get this, right? Y minus 1 H equal to 0. But Y is arbitrary. We can take it not equal to 1. So that implies that H must be 0. Okay. So in the similar way, YB is equal to 0, right? So this will determine that your matrix must be scalar, because as I showed you that B is 0, H is 0. In the similar way, you can perform the elementary operation here. That will be equivalent to perform the elementary column operation in the third, right? So comparing, you will get C and F, right, will be 0. Okay, so all the non-diagonal element in this way, you will find that they are non-zero, right? So if you want to prove it for the case of n cross n, just listen me carefully, okay? Perform elementary operation by multiplying some non-zero element in ith row, okay? Just multiply ith row. So when you multiply ith row of matrix, say you get this matrix, okay? Then this will be equivalent to, this will be equal to the matrix obtained by performing the same operation on the corresponding column, right, in the ith column. Then you can compare elements and get a lot of elements equal to 0, right? All non-diagonal, I mean non-diagonal elements will be 0, like that. So whatever I have shown here you for 2 elements, you can do this for all 9 non-diagonal elements, and you will get that all the non-diagonal elements are 0. This is just calculation, okay? That's why I'm not writing it here. Okay, right? Hope you are understanding this. So, and so our matrix must be look like this: ABC 0 0 0. So now I leave it for you. Oh, so can you see my screen? I think I can't see in the, yeah, you can see, right? What I have written here?
It is hanged.
It is? What is there?
It is
Okay.
only A, B बराबर A.
Right. So can you, I mean, decide now that why, can you determine? Yeah, can you let me know why A, B, and C will be equal? Yeah. Okay. So swapping ith and jth column, jth row will be equal to swapping ith and jth column, right? So see, yeah, let me tell you. Okay, so suppose you have this matrix. Okay, just swap its 1 and 2 row. It means you have multiplied by a elementary matrix. Okay, so that will be equal to by the commutativity. So it must be equal to swapping column 2 and 1. So if you swap column 2 and 1, then what you get? Here B, here 0, here A, 0 0 0 C, and compare A and B. Then in this way you get A equal to B. In this way, all the diagonal element will be equal. Okay. So do you know what do we do? What did we do? We just multiply it by a elementary matrix which swaps I and 0, and that will, if we multiply from here, that will swap ith and jth column. Okay, then compare, we get that element A and B will be equal. In this way, we will show all the elements to be equal. So the matrix must be scalar. Okay, this will look like for A. Okay, so you can do that home. If you don't understand what I said, just I mean, do it by calculations. Okay, it is nothing more than calculation. So this is done. So this is true. Okay. So your matrix at last comes out to be scalar. Okay, so now I have a question for you. So suppose you have the space of all 20.
The screen is not visible.
Yeah, it's visible, I think. I can see it. That might be the problem might be at your end. So
Yeah,
yeah,
visible.
So yeah, it's visible, right? So what is the question? Question is that you have a space of all 2025. Okay, because there must be a question involving 2025 integer in your TIFR exam. Okay, that's my prediction. There must be. Okay, so now consider all those matrices which commutes with all idempotent matrices. Idempotent, okay. Idempotent means, you know, A square equal to A, whose square is equal to itself. So satisfying these kind of metrics. So just answer me tomorrow, okay? So what is the answer of that? I mean, what kind of that matrix would be which commutes with every idempotent matrix? Okay, so for tomorrow, this is the question. Okay. Okay, so now let's come to the next question. Yeah, so this going to be very interesting question. You know, I think most of you can solve it. So, okay, so how many of you can solve it by the way? But a question after this, that will be very interesting. After this, I will ask a question, okay? So let's see the solution of this question. Okay, so this type of question you must solve in the exam. Okay, how do you solve this? Okay, so for this you must know that this, whenever you have a ring, commutative ring with unity, and you have an ideal I, so I'm not writing it here, just saying, okay, R modulo I is integral domain if and only if I is prime ideal. Keep that in mind. It's a very useful. You should know this. If you are studying algebra, then you must know this. Okay, this is very important. So see, now we are asked that this polynomial is, so I no need to tell you that from which year this is. So you must have inferred that. Okay, so this will be an integral domain is ID if and only if x to the power 4 plus x square plus 2023 ideal generated by this is prime ideal, right? And in a PID, a prime ideal is generated by, please let me know about it. Anyone? Yeah, you can speak, just I would not name. In a PID, a prime ideal is generated by
Irreducible element.
A non-zero prime ideal, I should say, right? Irreducible element. So we just need to check that this is irreducible over R or not, right? Irreducible or not. So everything is natural, right? I'm not doing anything. So you can think like that, right? So irreducible or not. So what do you think about its irreducibility? It's reducible. Okay, in fact, let me tell you a fact that every polynomial whose degree is greater than 2 is reducible over R. So it might be asked you in an interview also. So how do you show that any polynomial with degree greater than 2 is irreducible? Sorry, reducible. Okay, let me show you. That's very easy. Okay, see. So see, suppose degree of fxh, degree f is greater than 2. Okay. If it has even degree, then we are done, right? Because, sorry, odd degree. Because if degree is odd, then we are done, right? Because it has a real root. And a polynomial with a root in field is always reducible. Because we can divide by, say root is alpha, then we divide by x minus alpha and reduce the our polynomial, right? So say that it has even degree, but if it has even degree, If it has a real root, then again we do the same thing. If it say that no real root, then what happens? Alpha is a complex root, then alpha bar is also a root. Everyone knows that, right? If you don't know this, then you should know. I mean, this is very trivial fact, right? So see, x minus alpha and x minus alpha bar will divide your polynomial fx, because alpha is a root and alpha bar is a root, so both will divide, so their product is divide. And this polynomial x is what this is, like this, alpha bar divides fx. But do you know that this alpha bar is always real? If you add a complex number with its conjugate, then you get 2 times of real part. And when you multiply a complex number with its conjugate, you get the square of the modulus. So these both are real. So a real quadratic polynomial divides fx. Right? So it means that you can factor fx, a quadratic, something like, into gx. So it again reduces. Okay? Right? So any polynomial with degree greater than 2 is always reducible. This might be very helpful in the exam, okay? Because such kind of questions may be there again. That might not be the same, but it can be used somewhere. Okay, so see, so it means that this is reducible polynomial. If this is reducible polynomial, then this is not going to be a prime ideal, then this is not going to be a integral domain. So in this way, we found that this is false. But now, so I want to ask you some question. Okay, so you will answer that. Okay, so then we will come to this question. So can you think that, say, okay, you have a cubic, you have a, say, quadratic over Q. Say its covariance A0 over QX. All real roots. So it is reducible or irreducible over Q? Please below your hand.
Reducible.
Reducible, okay. So think for a moment. Yeah, this might be reducible. Is wrong. Okay. That only mean that that might be wrong. Okay. All real roots. Think for 2 minutes at least. This is what
Sir, not
extra thing we are
always.
doing. Not always. Okay. Noted. One says yes, one says no. I note your name also. Okay. So what do you think, others? Any comment? Okay. Just don't afraid of being incorrect. Okay. We are learning. So
Yes,
if
sir, sorry, it not always reducible. I
okay.
think it is R of X.
It is
I think it is R of X, so I say it is reducible always,
R of
but may not be
X.
reducible.
What does that mean, R of X? It is over QX. The polynomial you have to take Q over QX. Okay, you cannot take over real. I mean, a polynomial with coefficient from Q, which has all real roots. Okay, so give me an example with a polynomial which is irreducible and has all real roots.
Sir, x to the power 4 plus 1.
Huh? Yeah. Oh, but I can't listen you. You are not audible.
Sir, x to the power 4 plus 1.
Okay, but all of its roots are real. Do you think? How do you think? How do you say it's all roots are real?
Sir, x square minus 2.
X square minus 2 is 2-degree polynomial, right?
Sir, x to the power 4 plus 5x square plus 6.
Why that has all real roots?
That is x square plus 2 into x square, sorry,
But
x square minus 2
but
into
then
x square minus 3.
right. But you have
I'm
given me
sorry.
the example of reducible. You already you are reducing that, right? X squared into something. That means that's reducible. It's
Yes.
interesting, right? Yeah.
Yes.
Yeah. Someone, some girl said something.
X to the power
X
4
to the
plus
power
2x cube, 4 plus
2x.
2x cube plus 2x square plus 2x plus 2 equal to 0 by Einstein criteria.
But how do you? Yeah, right. That must be irreducible. But how are you sure that all the roots of that are real? That might have
Because
complex.
the polynomial is a degree of 4.
Polynomial is of degree 4 and over q, but the roots might lie outside real numbers, right? That is irreducible, right? Okay, so think about it and let me know tomorrow. Okay. So that's what I'm saying, that's very interesting.
Sir,
Yeah.
x minus root 2 का power 4.
X minus root 2 का power 4.
का whole का power 4.
But
It says root 2 as 4 minus root 2. Sir, x.
X
Sir,
क्या बोला?
x minus root 2 का whole का power 4.
But that is not a polynomial over q. ये तो q के ऊपर है नहीं. That is over r.
Yes, sir.
Yeah. So try it again. It's
Okay,
very
sir.
interesting, right? Okay, so you have to find yourself what is the answer to this question. Okay.
Okay, sir.
Sir, x fourth minus 5x square plus 6.
But okay, that might be. But okay, I will ask you tomorrow again. So let's give a chance to others also. That might be okay. So okay, come to this question. So I will ask here also interesting question. First, solve this problem. This problem is very, very good. So really, this was asked in TIFR 2017. Okay. So what it asks, how many also isomorphism classes of associative rings with identity are there with 35 elements? Prove your answer. So what is your answer first? You will let me know the answer. I will prove. So how many rings are there, do you think? Okay, so let me solve it. Okay, so see what we have given, that the ring of R, its order is 35, right? So 35 is 7 into 5. Okay, so I want to know that how many rings are there. First, I would like to see what rings do I know. Okay, what rings do I know? So you know this ring, right? Do you know any other ring there than this? So keep trying to know. You will never be able to know that because there is no other ring of order 35 than this. Okay, how do you prove this? See, very interesting. So as an additive group, so okay, what is the order of one? So how many of you know about the characteristic? You should know about the characteristic. I should not ask that how many of you know, because I have pre-assumed that you know all these things you are going to offer in the TFR exam. So characteristic of a ring is a number. You can just say that here in this case, that is just the order of unity. Okay. I mean, whenever say characteristic something a positive integer, when you add any element that times, then it is 0. Okay, such an element, such an integer need not exist. In that case, you say zero characteristic. But in case of finite, it is always possible. So what is the characteristic of this ring? The order of unity, right? Order of unity. So what would be the order of unity?
35.
35, right? Why 35?
If you add 1 35 times, it will be 0.
Right, but that doesn't mean that order going to be 35. It means that order going to be 7 or 5 or 35. Okay, right? Good guess, but you should know how to prove that. See, so the order of unity can be additive order, okay? Can be 7, 5, and 35 and 1. 1 is not possible, you know that, right? Because additive order of 1 is 1, additive order of 0 is 1 only, okay? No other element can have 1 order. So if order of unity is 7, so this implies 7 is characteristic, right? 7x is equal to 0 for all x in your ring, right? So this further implies that every non-zero element order is 7 for all x which are not 0, right? If you add 7 times some element, you get identity element. What does it mean? Its order is either 1 or 0 or 7, but I'm excluding the order 1 element. So any non-zero element has order 7, but that's a contradiction to some famous theorem. What is that theorem? Contradiction to a famous theorem. Just name that. All element has order 7 and its order is also divisible by 5. No element has order 5. This contradicts the famous Cauchy theorem, right? Because Cauchy theorem says that if you have a prime which divides the order of the group, then there must be an element of that order. But what we here get, that every non-identity element has order 7. That's really a contradiction. That cannot happen. There must be element of order 5 and order 7. So contradiction. Contradiction to Cauchy theorem. To Cauchy theorem, right? And so what does it mean? In the same way, 5 cannot be the order of unity. So the order of unity is 35. So your ring is this. 0, 1 times unity, 2 times unity, because order is 35. So everything, these all are distinct. At last, 34 times unity. So this is just a natural isomorphism to get 35. Okay. Send n times 1 to n. Okay. Right. So now about the interesting question. Let me ask you that. So is it clear? So yeah, we are about to end of the session. So let me ask you an interesting question again, okay? I mean, whenever I will discuss a question, then there will be an interesting question based on, I mean, related to that in some way, okay? So you have Q modulo Z. How many of you know about this group? Everyone who have studied abstract algebra, because this is very, very, very interesting group, right? You also know there is an interesting property of this group, very specific property that was not usually found in the real numbers, integers, in Q. Okay. So now can you find a ring? R is CRU. Okay, write the question, okay? R is a CRU. So can you find a CRU, commutative ring with unity, such that there is a isomorphism from this Q by Z to R plus group isomorphism? What is the question? Question is that is Q modulo Z isomorphic to the additive group of a ring with unity, commutative ring with unity, okay? So this is your question. So I'm not asking you answer now. Very interesting. You can try it at home. This might be in your TIFR exam also. Such kind of question might be there. Okay, so now at the last question of this session. Okay, so and how do you solve this question quickly? Okay, I'm always letting you know that how do you solve questions quickly? How do you save your time in the exam? Because in the last, when we discuss about this, this question which involves this, then we use the correspondence theorem, but that thing can also be done by calculation. So here is the same thing can be done by calculations. You can calculate and prove that this set of all polynomials in the range, sum of which coefficient is 0, is going to be ideal, but that will take your time. So we should not do that. If we have tools, if we learn abstract algebra, what is to prove some set is ideal, right? Standard way. So what is that? So see, so first of all, the set is, let me say that okay, this is the polynomial of zx for which f1 equal to 0, right? Sum of coefficient of polynomial is just f1, right? Put 1 on that and get the sum, right? Suppose you have a polynomial ax square plus bx plus c, then sum of coefficient is just equivalent to putting 1 in place of x, right? Yeah, so we have asked that this set is a or not. Is there a way which shows that this is kernel of some homomorphism? Yeah, right. You know about some homomorphism. Evaluation map. You must have known about that. So define from zx z which sends f2 its evaluation at 1. This is called evaluation homomorphism. Okay, and the kernel of this homomorphism is nothing but those polynomials for which f1 is 0. This is the definition of poly. So this is an ideal, and you are done. You have done this question quickly. Okay, so by the way, I have let you know the solutions of the questions. How do you solve these questions in exam? You can eliminate, because in the first question, so we have first question, what we have done here, we see that elimination is very useful, right? First we eliminate this quickly, because this cannot be true, because if this is true, then this is true. Then we eliminate, once we know that this is incorrect, then we try to make a counter example, and this is incorrect, this is incorrect, right? And we are done in the exam. So in this case, then this is your work from home, for home, not for the exam. In this way, you should know how to solve quickly in the exam. So I think that I should stop today. So we will be continue from tomorrow at 8:30. I suggest you to join at 8:30. Okay. So yeah, I would stop here. So this is all for today. So see you tomorrow. Okay.
Okay, thank you, Lalit.
So,
am I audible?
Yeah, you are audible.
Okay, thank you, Lalit, for this today's session with a good collection of problems from abstract algebra. Now, I think for the participants, you can share, if you have anything to ask, you can ask. We can spend 5 minutes for the discussion if you have anything to ask.
Yeah, obviously. I think participants would ask, right?
Yeah, dear participants, it's a time for you. You can.
I have because I have asked a lot of things in between, right? So yeah.
Okay. So, dear participants, feel free to share your feedback, or if you have any query, you can ask it now. So feel free to share your feedback with video and audio. Please unmute yourself and share your feedback. Of course, your suggestions also.
Sir, you asked us to remind about something at the end. You were going to share something.
Oh, okay.
During that problem, you said.
Yeah, what I wanted to say that when you will come back to the, so I will be discussing tomorrow the problems from not from 2024. Let me give you some reference where you can see those. TFR 2024 solutions. I will be discussing the problems from 2023, 2022, right? And like previous year problems, previous years from them. So, okay, so wait for a minute. Okay, let me give me 1 minute just to present my screen. So let me show you that how can you access those free question solutions. Okay, so yeah, let me see it. Okay, it will take me 1 minute only. Okay.
Sir, you're muted.
Yeah. So what I said, I'm muted. Yeah, am I audible now?
Yeah, yes.
Yeah, so what I said, you just go to the YouTube and search this 𝕃𝕒𝕚𝕚 mathematics. Once you go to this channel, go to the home page of this channel, then you will find here solutions listed. In the second number, TFR solutions are there. Click on that. Once you click on that, click on this TFR 2024 solutions. Okay, here will be complete playlist. All solutions I have discussed in detail. If you want to see them, just see about these 2024 solutions. Okay. I will be discussing solutions other than 2024. Okay, from tomorrow. So yeah, that's what one thing I also wanted to let you know that I said that there is a good problem in TFR 2020, right? So just click on 2020 and was that problem. That is very good problem. QX quotient rings of QXY. Okay, so that's what I wanted to tell you. Thanks for reminding me. Yeah, so. Yeah, let me stop sharing the screen.
Okay, others, feel free to share your feedback or ask questions.
Sir, am I audible?
Yes.
Hello, sir. Sir, as of now, my preparation level for TIFR is not very good. So, what would be your suggestion for last 1 week? What would be my strategy? Should I be referring books or should I stick to
No. You should
questions?
not look at the books now because it's not time to, you go to the book and read, then that will not give you anything. So, but you can do that. So, are you a PG student or UG?
Sir, I'm a UG third year student.
UG third year student. So, what courses you have done so far? Abstract algebra, real analysis, and linear algebra?
Yes, sir. But even in abstract algebra, I have done only very things that were about group theory only.
Okay, so I will suggest, see, in the TFR, TFR is such kind of problem where the questions are such that they are just they can be solved just using the definitions. I have seen a lot of questions, and the merit of cutoff of the TFR is not very high. Just if you solve 20 questions correctly out of 40, then you will definitely get a call. Okay, so whatever you know so far, just try to apply that and just try solving all the problems. So what I told you about the channel, you can go there and just see the TFR solutions in detail, and you can see there. So I have discussed there in detail where you will find the proofs of each thing and everything. So you can go into X speed because you don't have much time now, but whatever you know, and try to, utilize that thing only now. Don't read the books, because the books will, for reading books, you need enough time, right? You cannot do that in 6 and 7 days. So now for you, I think my best suggestion would be just try problems as much you can do. That would be useful for you, and just attend these sessions. I will definitely be keeping in mind that the students who are not with very good preparation are also attending this session. Yeah.
Yes, sir. Thank you.
Okay, thank you, Praveen. Yes, Gopika.
Am I audible?
Yes.
Sir, my name is Gopika. I'm from St. Thomas College, Thrissur. I'm also a third year BSc Mathematics student. What you said earlier, I'm also searching for a last week preparation strategy because for the previous 1 week, I have been practicing the previous year questions of TIFR exam. And I understood that I have a lot to cover because the courses which I completed in my college, like my friend told earlier, we did not cover a lot of abstract algebra. We covered all about proofs and only the basics of ring and all. So I think what you told now is applicable for me also. I think I should do more previous year questions, and I think your YouTube channel will be useful for me. Thank you, sir, for the suggestion. Thanks a lot.
Yeah. Right. And one thing I would like to add, that if you don't have covered much of the syllabus, don't worry, okay? So you have 40 questions. You don't have to solve all the 40 questions in the exam. You just try to solve 20 questions and did that correctly. Okay. So when I qualified my TFR exam in my MSc, I just solved 31 questions and all are correct. I did not touch any 9 questions. Just solved 31 questions. Okay. So although I have prepared very well because I was in my master's, so what do you need to solve? And sometimes you will find the problems which are from very, very basic definitions, number theory questions, and just the definition based question, the countable group question, countable set questions, right? We have discussed a question which involves about the countability that just involve constructing some, basic examples of the functions that does not involve very much, right? So such kind of questions you will find that. So whatever you have learned, utilize that. Okay. So don't worry about that. Don't think about that. I have not learned this thing, so that will create a problem. No, they're not going to create a problem. If you have, covered 75 of problems, if you know the definitions around 75%, then that would be enough. Okay. You just have to practice. Practice is very important, that you solve all the previous questions. So that is very important. That will give you an idea how to tackle problems in the exam. Yeah.
Okay, sir. Thank you.
Okay, thank you, Gopika. So, Lalit, I think we can wind up today's session.
Yeah.
Okay, so tomorrow, what is your planning? Which area you would like to?
I would, if students wants, they can send their questions to me. That I would not worry about the area. That might be from any area. Just send it to me, students. If you, just send to sir about, by 12 a.m. tomorrow. Sorry, not 12 p.m. tomorrow. Okay, 12 p.m. tomorrow. They will send to me, and I will discuss all those also. Okay. So from otherwise, I will, take. I will choose problems. So what I think that would be good for tomorrow. But what I said that please, practice 2024 problems that, might be connected to that.
Actually, majority of the participants are, I think, are degree students, and TIFR examinations common for both PG and
yeah.
degree students. For integrated PhD as well as PhD, they are having the same examination.
Right, but the merit is different.
Yeah,
Cutoff is different.
of course, but the people maybe get feared by seeing all these questions with it. Okay, that may be.
Yeah.
Yeah, for a degree student, they are at least in Kerala, they are not studying that much about ideals and all these abstract algebra. They are simply studying only the group theory and all that.
Group theory and the basic real analysis and basic linear algebra would be enough because if someone did not study some specific topic, that doesn't matter. I think so. One need not to solve full syllabus, prepare full syllabus. Yeah. So what TIFR exam requires is that requires some IQ, and you should know that how to, create something. Intuition should be very good, and how to guess, how to eliminate, that kind of things very much useful, I think.
Yeah, mathematical mind is required.
Yeah, right.
Okay. Thank you,
Thank you.
Lalit. Let us wind up here. Thank you, everyone.
Can you tell
What
Yes,
the
Prakash?
channel name?
Sorry,
Kindly, please, can you tell channel name, YouTube channel name?
Okay. Yeah, Lalit.
Yeah, I will send link to sir. They will forward to you. Okay.
Yes, sir. Yes, sir. Thank you, sir.
Okay.
I think the name is
Good night,
difficult to pronounce.
sir.
Yeah. Okay. So see you tomorrow at 8:30 p.m. all. Yeah. Give me permission to leave.
Okay. Let's wind up here.
Yeah.
Is there any Telegram channel?
हाँ क्या बोला?
Is there any Telegram channel or WhatsApp channel?
नहीं मैं सभी भेजता हूँ आपको. I will send you all the things. Okay. Sir will forward you. Yeah. So by tomorrow class you will get all these things.
Okay. Thank you, everyone. See you tomorrow. Good night.